Progress.
All right, folks. I think I'm going to be able to make these videos a little bit quicker. I pre-wrote everything. So 3-2, section 3-2, we're looking at derivative as a function. Now, so the derivative function, we're going to call it f prime of x. It's the derivative of f of x, and it just requires that the derivative exists at every point on the domain of f of x. And the general form of it is, we have it right here, this right here, where we're just going to do any x rather than x at a particular value a. We say f of x is differentiable at a if f prime of a exists. We say f of x is differentiable on some set S if it's differentiable at every point in the set. And then we just say the function is differentiable. It's a differentiable function if it's differentiable at every point in its original domain. Now let's take a look at a couple of them. Pause this video as you need to write the stuff down. First example we'll look at is f of x equals the square root of x. You'll see as we go through it, if we set it up with limit as h goes to 0 of f of x plus h minus f of x over h, we have square root of x plus h minus square root of x over h. We have to, when we have radicals, we multiply by the conjugate. And the top ends up being like an a squared minus b squared here. And so we get this area, and the x and this negative x are going to cancel. And we're just left with h. Those h's cancel. And we're left with this. Now we can evaluate it at h equals 0. When we plug in h equals 0, we just get a square root of x and another square root of x. When you add them together, you got 1 over 2 square root of x. And that's going to be f prime of x, starting with f of x equals square root of x. I told you this is going to go quicker. Having it all pre-written out, make these videos a little quicker for you. Then we take a look at, pause that and go over it as you need to, work out those limits. In fact, I recommend this one right here, this 2x squared plus 3x. Try to see what you get when you take the derivative. Find the derivative function for f of x, 2x squared plus 3x. All right, so if you go through and do it, this is our f of x plus h. And this is minus f of x. X plus h squared, I did some side work over here. See, if you plug it in with the multiplier of 2, we get this. So we get 2x squared, 4hx plus 2h squared. And then we distribute the 3x, 3 to the x and the h. I'm going to get rid of those lines just to make it a little bit clearer. You'll notice the 2x squareds cancel out, the 3x's cancel out, as they should. Everything left has a factor of h in it, which we can factor out. And when we factor it out, those cancel. And we're just left with this. And now we can plug in h equals 0. So we get 4x plus 3 equals f prime of x. So now we can have derivative functions. And in 3.3, we're going to learn a shortcut way of getting these rather than doing the limit every time. That was really quick. I'm going to go on and do notation and graphing at the same time. So Isaac Newton came up with f prime of x, but there was another actor on the scene at the same time, Leibniz. And he came up with a different notation. It's based on the slope. So the slope is a change in y over a change in x, and we use this triangle symbol for change in. But triangle is delta. It's the delta letter, or capital delta letter in, I put a dot over the A like it's an I. It's a capital delta. So it's called delta y over delta x. And so he came up with dy dx here. And it's just doing like the limit as delta x goes to 0, the denominator goes to 0, is the same setup, really. It was when you look at, compare it to limit as h goes to 0 of f of x plus h minus f of x over h. It's the same thing. This is doing like the version with the f of x and f of a. So he came up with like, so not Leibniz came up with dy dx. Newton was f prime of x. Some other notations are y prime. It's, you kind of get this one. It's kind of like factoring out the dx, d over dx, but it's not the same thing. It's more like an operation, but it looks like we factored it out. And like, since y is f of x, it looks like that notation as well. So since f prime of x represents like the change, what's happening in the change in f of x, it actually shows up in the graphing of it too. So f of x equals square root of x. Notice it starts steeper and tapers off. And that's for f of x. And when we look at the derivative, it starts steep, but it's decreasing. Because the change is decreasing. Delta y over delta x is decreasing. That one's a little harder to see. It's a little awkward graph, but one we did earlier is f of x equals 2x squared plus 3x. So I graphed that here. That's that line right here. And one handy thing to notice about this is wherever the tangent line equals 0, the derivative equals 0. Well, the tangent line equals 0 right about there. The slope of the tangent line is 0 right there, which means our derivative, f prime of x, is the orange line. It's 0. Okay. And then if we look at the left side, the slope over here, like for less than that value, the slope of f of x is negative, but increasing. Like it's pretty steep here, less steep here, much less steep there. I need to use a different color for those. It's like steep here, less steep here, even less steep there, flat here, going up here, and starting to go up more and more. But the actual change is a constant change. Over here, the slope of f of x is positive. And that's why over here, like this section of the line is greater than 0. And on the left section down here, it's all negative. That really clutters up the image, so I'm going to erase that stuff, but that's really what's going on. So we can take advantage of that here. I put this in over here so that we can practice. So like right here, oh shit, got the wrong button on. Let's do that. There we go. So right here, we've got a flat line for the tangent. And right about here, we've got a flat line for the tangent. So f prime of x will have a 0 there. So the m tangent equals 0 is where f prime of x equals 0. So we got those 2 points right there. All right, so in this region, right here, we can see that the slope is going down. And then over here on this side, and over here on this side, the slope is going up. So where it's down, it should drop down. It should be in the negative region, because recall, this is the negative region and this is the positive region. So it's going to drop down, but it's got to come back up and do that. And it's going up. It's positive over here. It's negative here. And over here, it's positive again. And you'll actually be able to find right where this change is in a little bit. This change here is where the derivative flattens. And so we can look at the second derivative. Ooh, we want to see where that goes to 0. And so like you'll be able to see where this change is called concavity change. We'll be doing stuff with that later. We're not ready for concavity yet. But that's kind of what's going on here. Let me pause the video and make another.